In the ancient past, before the first stars formed, all was darkness, and the universe was a very different place. But there may have been strange dark stars in that primordial era at the beginning of time. They say 13.8 billion years ago there was a giant explosion and the universe came into existence, and sometime later stars and galaxies formed. It wasn't truly an explosion, even if the early universe of that era was more terrifyingly energetic than ground zero of an atomic bomb blast. And indeed it was a while after the Big Bang before things spread out and cooled down enough to even resemble the surface of a star, let alone a place where stars and planets existed. That early universe before the stars wasn't dark back then. The first few seconds it was too hot for nuclear fusion to even occur, that process that requires such insanely high temperatures and densities that we are just barely able to achieve them in a lab, and whose upper ranges are at the cores of supernovae. It took a minute just to spread and cool enough to get into that range. Almost all the matter of modern times comes from this period where those early protons banged into each other, when it was just cool enough to stick together and form neutrons and deuterium, which could fuse to form helium and a tiny bit of lithium. Had we spread even a little slower, there might have been no hydrogen left to form stars. Around 10 or 20 minutes after the Big Bang, things had spread and cooled enough that fusion wouldn't have been occurring anymore, but still around 1 billion degrees. That is hotter than the core of our own sun, or even more dense and short-lived ones. But in reality, stars fuse very slowly, so not even 1 in a million of those heavier Big Bang-era particles would have been formed after this window till when the universe finally cooled enough to be dark. 1 year after the Big Bang, the whole of the now observable universe would have fit into a volume similar in size to our galaxy, and that's already a density far lower than our atmosphere, let alone a stellar core. It was 380,000 years later when the temperature and density allowed neutral hydrogen atoms to form from lone protons and electrons floating around. At that point, the currently observable universe was closer in size to a supercluster at about 100 million light-years across, and was already down to densities we think of for outer space, even if far more dense on average than now. This period is opaque to us because of how bright and dense it was till then. This begins the era of darkness, when the temperature of the universe was finally colder than a star and no longer emitting visible photons, and yet matter hadn't clumped enough to make any stars for us to see. Those first stars, population 3 stars composed virtually entirely of hydrogen and helium, may have begun as early as 100 million years after the Big Bang, and the first galaxies not long after, but they may not have been the first stars, merely the first to power themselves on fusion. This is our topic for today, these early and hypothetical dark stars, and there's a few different types that have been proposed. They were very unlike stars of modern times and may have been composed of dark matter, which is why they are called dark stars, as they are generally not thought to have been dim. Indeed, the leading candidate for one discovered earlier this year, appearing as a possible early galaxy from back in this era, might instead be a dark star 1 million times more massive than our Sun and far brighter. While there are a number of hypothetical stars, our focus for today is the dark star and quasi-star, and those other versions hypothesized for the early universe. The dark star is dark matter-based, and the quasi-star black hole-based, and you might wonder how either works. And the answer is we don't know for sure, since we don't know what dark matter is yet, but one of the more popular candidates is the neutralino from supersymmetry models. Now, channel regulars probably know that I am not a big fan of supersymmetry or string theory, as they've not really got much evidence backing them yet, or really any at all, but they remain fairly popular with cosmologists as they do fit the available evidence as well as anything else we've got, and I suppose you could say I'm less unfond of them than most alternatives. This is no fault of cosmologists either. Reality seems to have conspired to make figuring the problem out and getting evidence nigh impossible. Regardless, supersymmetry seeks to extend on the standard model by introducing a number of additional particles like the selectron, the superpartner of the electron, as something like the parallel of what antimatter is, with a positron being the antimatter particle of the electron. All the fermions like quarks and electrons have an S prefix like that, squarks, selectrons, etc., while the bosons, like the photon and gluon, become the photino and gluino. There's a Higgsino and the aforementioned neutralino, which is a candidate for dark matter. What's neat about neutralinos is that they are their own antiparticle, and they annihilate when they run into each other, which would have happened more often in an earlier and smaller universe. The idea goes that early in the universe we might see a cloud of molecular hydrogen and helium somewhere between 4 and 2,000 astronomical units wide, several light days. So these are very big, on an order of red giants or even red supergiants or bigger, but far dimmer. The idea is that the cloud of gas would be warm and unable to collapse into a star because of those antimatter annihilations. Paolo Gondolo, the astrophysicist who proposed them, originally wanted to name them as a subtype of brown dwarf, as they would be in that infrared temperature range, but was talked into naming them dark stars as a reference to dark matter and an homage to the Grateful Dead song Dark Star, which amusingly is how I first heard about it. At the time they came out, I was in the army after leaving grad school and semi-intentionally not keeping up much on the field, but a friend from my unit who was a big Grateful Dead fan saw an article mentioning them and asked me about them. They were a neat-sounding curiosity and mostly fell to the wayside in recent years, as they'd be very hard to see and were very hard to model without any actual neutralinos to use in determining parameters like dark star mass, density, lifetime, and so on. That's where the JWST or James Webb Space Telescope came in, and earlier this year we had 4 extremely redshifted objects get spotted that were a bit anomalous in their behavior, particularly in being point-like. One of those was JADE's GS Z13-0. The JADE stands for JWST Advanced Deep Extragalactic Survey, and based on its redshift we assumed it was an early proto-galaxy. Indeed, with a redshift of over 13, a Z of 13.2, it was the oldest and most distant spectroscopically confirmed galaxy we had, and we see it as it would have been 13.6 billion years ago. All of those galaxies were smaller and more numerous back then too. Our own galaxy and Andromeda are both far bigger because they've been swallowing other galaxies for billions of years. But the thing is, while stars look point-like even under very high zooms because of how small they are compared to interstellar space, galaxies are of a fairly similar size to intergalactic space, so we still see their shapes even when viewed billions of light years away. This is where dark stars come back in, because we're talking ancient days, and few to no regular stars yet, and something that appears to be a very small radius compared to a galaxy. It's been suggested it could have been one of these dark stars, and one that was about 1 billion times brighter and 1 million times more massive than our own sun. Sadly, there's not much else we can say about them yet. They go into the neat phenomena category and offer some interesting possibilities for dark matter. There's little reason to think any would have persisted to modern times, so we're not likely to ever get a close look at one. If they were around, they would be recognizable by being large blobs of molecular space gas giving off telltale radiation in weird frequencies associated with antimatter collisions. As a side note, I've heard folks suggest we could have a twin reality where antimatter was much more common, much as it's rare compared to normal matter here, and if there was a leakage between them, it would be visible in this way too. Some older sci-fi played with this idea, though often a bit loose on the science. But they replace fusion as the source that makes the upper reaches of a star hot and glowing with sunlight. The same would be true of quasi-stars, our other topic for today, and they assume the star is gas being superheated by a black hole at the center. Now this is basically what quasars are, only scaled way up, and since primordial black holes are another common candidate for dark matter, I guess these could be considered a subtype of dark star rather than a separate category. Though that's more of a hand wave at me not wanting to expand the cool-sounding title of the episode to be Dark Stars and Quasi-Stars at the beginning of time. Also an interesting name, as a quasar is short for quasi-stellar object, so quasi-star being similar to a quasar makes sense. Why isn't it a quasar? Well, it's not a mass thing. Quasars are enormous black holes on an order of 1 million solar masses, versus the few solar masses of a normal new black hole birthed in a large supernova. But quasi-stars are thought to be of similar mass. Quasars are also now nearly extinct in the universe, peaking out about 10 billion years ago, but we think the quasi-star would have only been around in the early days. Here we imagine an entire nebula worth of hydrogen and helium, but in which star formation hasn't occurred yet, nor any big supernovae to blow curtains through it to set off star formation. We believe back then, before we had any heavier elements, you could have gotten true juggernauts of star forming. Those metals that modern stars have alter their fusion properties quite a lot. We believe we might have gotten stars not tens of times more massive than our Sun, as the largest star nowadays, but some tens of thousands of times more massive. So massive that even when a supernova occurred, which would not have taken too long, the force of that blast would not have ripped the immense star apart, leaving a huge gas cloud around a new black hole and a protostar with a black hole in its center. Matter falling into that black hole will release huge amounts of energy and heat to the area around it, pushing matter away until an equilibrium was reached, matter falling in just fast enough to produce enough energy to blow other matter away, similar to how fusion equilibrium in normal stars occurs. And we've talked before about using this trick to generate very long-lived artificial stars inside gas giants or brown dwarfs. See our episode Making Suns for more discussion of that. We don't think this would have been stable for long, possibly several million years, but the black hole would keep growing while the sphere around it cooled, eventually leaving an intermediate mass black hole. They would be big and look like a very, very large star, big as the solar system and bright as a smaller galaxy. There are, nowadays even, enormous stars millions of times brighter than our Sun and so huge they'd swallow our whole solar system. But they would not be similar enough to the quasi-star in spectrum and radius to be confused with each other. A tree and a house might be of similar dimensions and composition, but you wouldn't mix them up. Same here. What's particularly neat about them is they do operate just fine under known physics, and they could plausibly have been the first stars to form. They can't form now because big pristine stretches of homogeneous gas aren't really around anymore. Partially it's because once you start having lots of galactic structure and stars going supernova, you get lots of uneven pockets, and so some big glob of gas massing a million suns is likely to have a ton of big stars form in it as it collapses, which will supernova and blow it apart and set off more star formation. There is also, as I mentioned, a component of having lower metallicity in that early universe, as well as things being denser and warmer. It's not taking as long for stretched out gas clouds to condense into stars. If you want to know more about how gas clouds collapse into stars, it is a complex and still not perfectly understood process, but revolves a lot around what we call Jeans mass and Jeans instability. The hotter a gas cloud is, the more its own pressure pushes it apart. So more of that in the early universe, which was hotter, and the bigger it is, the more gravitational energy pulls on it, and the more that energy gets released as heat, pushing back on the collapse. And the short form is that those contaminant metals of dead stars allow such gas clouds to cool quicker and thus change the maximum size stars can be by lowering it. Hence, big stars could form back then and wouldn't have the life cycle we have now. Since we have yet to confirm the existence of any population 3 stars, those with no metals, it is a little hard to know, and of course no star of that size would still be alive these days. I like the idea myself, but that doesn't necessarily make it true any more than dark stars, and if you're looking for a deeper dive on quasi-stars, there was a great paper on them about 10 years back, Massive Black Hole Factories, Supermassive and Quasi-Star Formation in Primordial Halos, in Astronomy and Astrophysics Volume 558. But the neatest thing of all is that we still don't know where all those supermassive and intermediate mass black holes came from that are so vital to how early galaxies formed and for driving star formation in general, and those early quasi-stars are one possible candidate for them, and a fairly strong one in my opinion. I like the idea of some star so titanic it dwarfs modern stars like they do planets, and in which early black holes formed and rapidly chewed their way up to intermediate or greater mass, and became the linchpins of the proto-galaxies that came after. One other possible source of quasi-stars to mention before closing out. We speculate about small primordial black holes forming at the beginning of the universe as a possible type of dark matter, and currently assume they can't be of a certain mass ranges, as otherwise we would see their expiring Hawking radiation. We covered them in detail on our episode on black holes and dark matter last year. But it is possible early black holes formed in the opaque period we can't see, and may have tended to get fed up to certain discrete mass ranges, and that some of these became the cores of a dark star or quasi-star-like bodies. And as I mentioned, they also make use for artificial suns if you can make micro black holes. And you can then control the feed rates on those for greater stability. So were these strange and enormous stars around at the beginning of time? We don't know yet, but thanks to the James Webb Telescope, we have some intriguing new bits of evidence to contemplate, and all learning more every year about that primordial time of intense light followed by darkness before the stars we know came to be. An interesting and mysterious epoch of time. And thank you for letting me have some of your time today to talk about them. We're going to be continuing our discussion of primordial eras with a look at primordial civilizations this Thursday, along with the possibility of leftover doomsday weapons and robot fleets. That's always been a popular storyline in science fiction, but it's getting creepily relevant. AI is everywhere now because it's so useful, but it's also useful to hackers or even companies and organizations that just like to gather your personal data and sift through it. There is no perfect line of defense for problems like this, but your first line of defense online should be a virtual private network like NordVPN. This lets you hide your IP address from sites you visit and hackers, but NordVPN helps further protect you with features like web tracker blockers and ad blockers, and threat protection to warn you about phishing links and dark web monitoring to alert you if passwords have been leaked. All of these features and more come with a robust VPN so you can protect your data and unblock region-specific content. The best part? You can try it with no risk. Nord has a 30-day money-back guarantee, so you can try it for yourself and decide. Go to nordvpn.com/IsaacArthur to get the 2-year plan and some additional months for free. So as mentioned, next week we'll be continuing our discussion of the distant past with a look at ghost armadas and primordial galactic wars. And in 2 weeks we'll be discussing harvesting entire planets, like might have been done by civilizations seeking to fight galaxy-spanning conflicts to create those armadas. Before that though, we'll look at creating worlds, not destroying or harvesting them, as we examine the early terraforming techniques and challenges that come after you arrive on a desolate new world. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or Patreon, or check out other ways to help at isaacarthur.net. SFIA's episodes also come out early and ad-free on our streaming service Nebula, like this month's exclusive episode, Caretaker AI and Genus Loci, at go.nebula.tv/IsaacArthur. As always, thanks for watching, and have a great week.